And so, what's that? That's probably true. There will be older versions out there circulating of essentially the same book, just without MindTap, that you can get. But no, so the actual MindTap itself won't be for any type. Hey, stop sharing. No, you can still see it. Okay. So the MindTap itself is just for y'all to get practice. So if you don't want to buy it, definitely don't have to. But yeah, good question. All right, what other questions do we have? Either about what we learned last time or about this class? Nothing? Feeling pretty squared away? Awesome. Awesome, awesome, awesome. So I will tell y'all in person here the same thing that I told the folks in person last time, in case you didn't hear. The administration is predictably very strict about masks, so please just make sure, I mean, all y'all are wearing masks here. If for whatever reason you show up without a mask, I'll ask you to put one on. If you still don't want to put one on, I'll pause class for 10 minutes, try to talk you into wearing a mask. If you still don't put on a mask, I have to cancel class. So let's just make it easy. Everybody seems to be in compliance. We're good to go. And everybody was in compliance for the health check today, so thank you all very much. Please continue to keep doing that. Makes my life a lot easier. All right, so somebody gives me an overview. What did we learn last time?
The difference between experiments and non-experiments and other experiments, for example. So causation and, sorry, I just lost it.
No, you're fine, totally fine.
Yeah, causation versus correlation.
Yes, causation versus correlation. And what's the difference?
Causation, for an experiment, you're measuring one variable that you are giving to a group of your subjects.
Mm-hmm.
You're trying to see what kind of effect that it has.
Yes, yes. So experiments are really good for establishing causation. We want to say that a change in one variable causes a change in another variable. We want to be able to say that wearing masks causes a reduction in the overall spread of coronavirus. Now, what's the flip side? What is a correlational study? Somebody else.
To determine whether there is a relationship between two variables.
Yeah. And so can you give me an example of something maybe we talked about last time or something else in the real world?
The murder with like steam objects in the ages of America.
Yeah, something, I don't remember exactly what it was, but yeah, you have all of these kind of spurious correlations associated with one another that really have no plausible causal explanation. But if you collect enough data, you're going to be able to find these correlations that really just exist because that's just the way of the world, right? And so one of the things we'll talk about this semester are things like data mining, right? And so there's some approaches out there where you collect a lot of data and then you just throw things together to see what correlates with one another. And that's not necessarily good science because, as you saw, we can establish relationships between variables that really aren't truly related other than the fact that they co-vary at different times. And so, yeah, correlation does not equal causation. Really important to remember that. Apollonia said measurement scales. Yeah, can you or somebody else give me an example of one of the measurement scales?
Interval scale.
Okay, and what's the interval scale?
The interval scale is, I mean, any scale that 0 is not a real value.
Exactly, yes. And so when we're thinking about things like Fahrenheit, right? So 0 Fahrenheit doesn't actually mean 0 temperature, right? Temperature is just a measurement of the amount of energy in the atmosphere or in any environment. And so 0 Fahrenheit doesn't mean there's no energy. It just means we've established some sort of arbitrary cutoff for what 0 is going to be. And I always use that as evidence for the fact that nobody should live really north of the Mason-Dixon line because it gets below 0 all the time. And we clearly established that really you shouldn't be living in any place where it gets below the base of what we decided it should be. All right, somebody else give me an example of what is nominal data? Yeah. Okay. Yeah, so give me an example. Yeah, so let's say an example of nominal scale would be, what's your favorite fruit? Some people like oranges, some people like apples. It doesn't make sense to have between those categories. There's no such thing as an apple-orange hybrid. Right, so we have these different categories. Yeah, and so I mean that also gets into a little bit of the conversation of how much of it is in fact a continuum versus these categories. Yeah. All right, so we have nominal. We talked about intervals. Somebody give me an example of ordinal data. The place you finish in a race, exactly. Yeah. So anytime you are in a race, you get 1 through whatever in that race. And that does indicate your place, but it doesn't necessarily mean that the distance between places is going to be the same, right? The difference between first and second place may be 30 minutes, but the distance between second and third place may only be 5 seconds, right? And so you have first, second, third, which indicates that order, but not necessarily that those are the same jumps. Yes, exactly. Apollonia and Esther. All right, so what have we talked about? Ratio. Yes, Amber, good call. Ratio. So what is ratio data? 0 has meaning, exactly. It's just like an interval scale, but the 0 has meaning. So when we think about things like height or weight, a weight of 0 literally means no weight. There's no mass whatsoever. Exactly. Good job, Esther. All right. For those of you all on Zoom, please do keep typing in questions and participating. I will certainly try to get to y'all as it comes up. Just reposition your chat so now I can see it as it comes up. But, all right. So any questions about that or what we learned last time? Good to go? Awesome. We are off and running in statistics. Come on now. I done screwed everything up. I'm moving that chat box over. Give me 1 second here. Too many mouses. Mice. Bring that chat box up. I appreciate y'all bearing with me here as we figure out all of these new technologies. There we go. Perfect. What's that? Yeah, computer hard indeed. Yes. Agreed. All right. Goodness gracious. Come on, team. Here is your fun fact of the day. Ravens in captivity can learn to talk better than parrots. Ravens are really good speakers, and crows are incredibly smart. Crows will also communicate if you've wronged them in any capacity. And so there are documented cases of somebody like throwing something at a crow, and then the day later, a swarm of crows, I think it's called a murder of crows, actually. A murder of crows comes and literally attacks the person. They have the recognition and they've been able to communicate.
Then why don't people have crows and ravens as pets?
Because they attack people, apparently.
All birds attack. Well, they're smart, so if you get in their favor,
Yeah.
and you feed them, they'll be happy with you. Yeah.
Oh, there you go. Well, I suspect it's probably a very superficial reason. Parrots are pretty to look at. Crows and ravens.
Okay, then why don't dogs have ravens?
I don't know. Maybe they do. Who knows? All right. What's that?
If it's legal to own a tiger, I feel like it's legal. I think so.
All right, we're no longer talking about statistics here. All right, bring it back in. If you are an undergraduate in psychology, and psychology is your major, you need to complete a course of study if you have not yet done so. All right, so we are starting today talking about frequency distributions. And I will move this chat box. All right, there we go. So we talked a little bit last time about the difference between like descriptive data or descriptive statistics, and then what a lot of the rest of this class is going to be, which is inferential statistics. And when we talk about descriptive statistics, those are really just giving us a description of the sample that we pulled from. And now we're hoping our sample is representative, so we can extrapolate the information from our sample to our population. But there are a couple ways we can do that. And so one way of giving people an understanding about your data is through this actual frequency distribution. And it's a mechanism by which we can actually display, either in table or graph form, the layout of the data. And so frequency distribution is just going to be an organized tabulation showing exactly how many individuals are in each category for the scale of measurement. So when we do that, it's going to present a much more organized picture of the entire set of scores in that distribution that we sampled. And you can think about this conceptually, right? Let's say we were doing a study on height, and we wanted to see if somebody's height affected their ability in basketball. Well, one of the first things we want to look at is, were the researchers good researchers? Did they get people of all different heights, or did they only get people 6'5" and taller? Right? If you only got people 6'5" and taller, chances are they were recruited to play basketball at least at some age and develop those skills. And so we want to be able to see, okay, did you in fact get people from Muggsy Bogues' height, which was 5'1" or 5'2", I think, all the way up to Yao Ming's height in the general population? Or did you just get the general population of those who are likely tall enough to play basketball? It also allows us to see where every individual in our population or in our sample relates to everybody else. Right? We have our own frequency distribution in our mind of height. Right? So how tall are you, Jace? 6'4". So when you see Jace, you know that, okay, he's atypically tall. Right? Because you have this frequency distribution. You have this prior in your mind knowing what the distribution is like. And so you know he's taller than most people. And there are a couple ways we can represent this. One would be with a frequency distribution table. So that table is going to consist of two columns. One is listing the category or scale of measurement. That'll be on the left. That'll be our X value. And another for the frequency. When I say frequency, what do I mean? Yeah, just count. Exactly. Just the number of times that is represented in the data. And I'll draw you an example in just a second here. But in that X column, you want to make sure that you are representing all the possible categories in the range of responses, and that it's organized, because then it allows you to truly see what is the spread rather than bouncing back and forth and back and forth. Okay, so I put those who are 6'1" next to those who are 5'3", next to those who are 6'4", etc. You want to do it from 5'1" to 7'1". And you also don't want to skip any values. Why might you not want to skip any values when putting this together?
Give it an accurate frequency and like relationships with the variables.
Yeah. So I mean, the goal with any sort of table and any sort of figure is to tell a story, right? You're trying to make it easy for your reader. And if you have a frequency table in which you're just excluding any value that was not represented in your sample, at a quick glance, somebody could be led to believe that you had equal distribution across your sample, rather than the fact that for a lot of values in your sample, maybe you just didn't have anybody who was from 5'8" to 6'2", right? If you exclude those, it makes it look like you do have people across the entire spectrum. But you're better off putting 5'8", 5'9", etc., with 0 next to that frequency. Yeah, you're absolutely right, Evan. Yeah, it'll skew kind of the perception of the data. So when a frequency distribution table lists all of the individual categories, all of the X values, we call it a regular frequency distribution. All right, so what does this look like? Let's say we've got our X over here. We've got our Y. And we're going to do the actual just heights, and we're going to limit it because I don't want to write everything. So we have 5'8", 5'9", 5'10", and 5'11". Nobody in our population is below 5'8" or above 5'11". And so in the Y, we are just putting the number of people that fit in each one of those categories. So we'll have 3, we'll have 2, we'll have 0, and we'll have 6. All right, and so that's just a frequency distribution table. In some cases, it does make sense to truncate the actual X values, right? It doesn't make sense to have everything in this X column go down to 0 inches, because nobody's 0 inches. You could, in theory, have it go all the way down to the world's shortest person and have it go all the way up to the world's tallest person. But so long as you encapsulate everything between the minimum and the maximum height, in this case, you'll be good on that X column. Sometimes the actual values, though, are going to cover a huge range of values, right? So let's think about SAT scores, right? The range of possible SAT scores is massive. And maybe you don't actually want to write down every single SAT score and how many people at UAH got that score. So what you'll do is just group those values together to make a more simple, simplistic representation of the data. So back when I took the SAT, it was still at a 1600. It's at a 2400 now. Is that right? Yes? No? I don't know. Huh. What's that? Yeah, the ACT I think is more common down south. But we're going to... Okay. Perfect. Well, let's just say 1600 because I'm a dinosaur. So maybe instead of going all the way from whatever the minimum is, you could get like a 400, I think if you just wrote your name, all the way up to 1600. Now we'll do, okay, how many people got from 400 to 500? How many got from 500 to 600? 6 to 7, 7 to 8, 8 to 9, etc. So now we've grouped them together, and that allows us a much better kind of glimpse into the data than having this massively long table. Because in reality, the difference between an 880 and an 890 isn't really all that big. The difference between being on average in the 800 group and being in the 900 group is fairly substantial. And so maybe that's where we put it. Or maybe we just do it every 50. There's no general rule of thumb for these sizes to make the groups, but as long as you have justification, you're better off. So yeah, like I said, in a group table, that X column is listing groups of scores, called those intervals, rather than the individual values. And so you can go with approximately 10 intervals, but if you get to the point where those 10 intervals are encapsulating way too much range, maybe it makes sense to expand it, or you can truncate it if you don't really have reason to have intervals that small. Sunny asks, is it possible to show the example given over Zoom? Because I don't understand group frequency. Yes, did that not show up when I drew on the iPad? Bummer. Yes, so it did. All right, so some of y'all are seeing it, some of y'all are not. So it should have been on the PowerPoint that it showed up. All right. Yeah, so Esther and Sunny, if y'all are still having problems if I draw on it again, let me know and we can figure out what's going on. Maybe on my end, maybe your computer, but we'll figure it out. So let's do a real quick critical thinking activity. Go ahead and make your own frequency chart or frequency table on some sort of observable characteristic of your classmates. For those of y'all on Zoom, you can either make it up or look at the pictures of everybody else in Zoom, etc. But go ahead and practice making one. You can do it off hair color, you can do it off computers versus not, etc. Take 2 seconds to do this. Yes, Sunny, I didn't make your group frequency. Sixteen more seconds. All right, so I'm going to go ahead and make one for using computers in the class. And so we have our X value, we have our Y value. And so I'm going to abbreviate it C for computer and NC for no computer. So see 1, 2, 3, 4-ish. And we'll count the iPad. So 5 computers. 1, 2, 3, 4, 5, 6. 6 no computers. And so you can see how when we talked about the frequency distribution initially, we talked about it on an actual scale, right? Or on a continuous scale. But you can also do it with categories, categorization, right? So let's say we made this, and instead of computer versus no computer, we did it favorite color. And so now we can count the number of people that have different favorite colors and represent it this way. And so you should all get a good understanding of why these sorts of tables may be beneficial, right? They help tell a story without requiring your reader to go through and sort through a whole bunch of text actually in the research document. And it gives you a good understanding. At a real quick glance, you can see it's about 50-50 split, right? You don't have to do much mental calculation. You know, if instead of 5, this was 1, you know, now you see, okay, most people don't use a computer, right? And so it becomes really easy. Your goal when you write these papers is to make it as easy as possible for your reader. All right, any questions about those sorts of tables? How to put them together, what they should look like?
Excuse me.
Yes.
I'm not sure what a group frequency table is supposed to look like. Could you like draw one now, please? Because I saw the one you just drew now about computers and not computers, but I didn't see the group frequency one.
Yeah, so I didn't make a group frequency one, but yeah, let me draw a group frequency example here. So let me cross this out. I don't know how to erase on PowerPoint, so just ignore everything I just crossed out. All right, so now we're going to do the SAT scores. And so SAT scores will be our X value, and then our frequency or our Y. We call that frequency. And so let's say we don't want to do the every SAT score. So now we're going to do, you know, below 1,000, 1,000 to 1,200, 1,200 to 1,400, and then greater than 1,400. Whoops. All right, so now let's say we sampled UA students and we had 2 that came in below 1,000. We had, you know, 17 that came in between 1,000 and 1,200. We had, you know, 36 that came in between 1200 and 1400, and then we had, you know, 3,000 that came in above 14,000. So does that make sense, Sonny, how we are grouping these different continuous variables into specific subsets and subgroups?
Yeah, thank you.
Of
I
course.
get it now.
Perfect. Apologies for not drawing it earlier. All right, any other questions? Awesome. Pretty straightforward. We are rocking and rolling. So we just showed how to do it in a table, but frequently tables still require some sort of mental calculation. People are inherently visual creatures, and so we like to have things represented graphically, right? You could see how it still took you a half second to look at my computer versus no computer example and get the representation and the relationship between those two groups. But I can also represent that in a graph that shows you right off the bat, oh, look, this bar is a lot bigger than that other bar, right? You're not having to make any sort of mental calculation of relationships. And so when we do this, the groups, the categories, we represent on the x-axis, as we always do with like independent variables in this class. And the frequencies we're going to list on the y-axis. And so when the score categories consist of numerical scores from either an interval or a ratio, that graph should either be a histogram or a polygon. And I'll show you examples of that in just a second. And so again, it's important to think about the fact that every time you make a graph, you're telling a story. I know that is perhaps the nerdiest thing you'll hear today, but you're really telling a story with your data, with statistics. And you want to be able to get to the point where somebody can look right at your graph, right at your figure, and understand exactly what you did without having to devote that much effort. And so histogram, I'm sure you all have seen at one point before. In the histogram, a bar centered above each score or interval that we've established, that group, so that the height of the bar corresponds to the frequency, and the width of the bar corresponds to the real limits. So we talked about real limits last time. Can somebody tell me what a real limit is? Yeah, so a boundary between numbers. Can you give me an example?
I can tell you that for 12, has the upper real limit of 12.5 and the lower of 11.5.
Exactly, yes. So yeah, you've got for 12, when you're thinking of just in whole numbers, from 11.5 to 12.49, right, in there. Yes, for all those of y'all on Zoom, exactly, the grading system. So an 89.5 is the lower real limit for an A in this class. And so you're just having it expand to touch the real limits in there. And so this is what it looks like, right? So you can see on the x-axis, we've got the scores. Let's say in the top case, you can only get 1, 2, 3, 4, 5. All whole numbers. You can see in the top right, we have created a table. And then now, in this graph, we have the frequency represented by the height of each bar. And you can see the bars reach from one side to the other. On the bottom, instead of having it as whole numbers, we've decided to group the kids together. So we're looking at children's height. And you can see this first bar right here on the left is 30 to 31 inches. The next one's 32 to 33. And so it's expanding such that in reality, the 30 to 31 really likely goes from 29.5 to 31.49, right? And the 32 to 33 goes from 31.5 to 33.49. And you can see how there's no gap in here. However, let's say we didn't have anybody in the 36 to 37. This entire bar would be down here. But we don't get rid of that, right? We still want that gap in there because it's telling the story, right? We don't have a perfect representation across all of the heights for these kids. And so you can see the relationship between the graph and the histogram. They're giving you the same information, but you can see how the histogram is presenting a lot easier picture of what's going on in your data than the frequency chart. All right, you can see we've got essentially two spikes here. We may even call this a bimodal distribution. We'll talk about that later in the semester. But it becomes a lot easier to see, okay, just quickly, 38 to 39 had the highest frequency. Boom, done, easy. We also then have polygon representations of the data. And in a polygon, we center a dot above each score such that the height of that dot on the y-axis corresponds to the frequency. So think about putting a dot right where the top of that bar, if you were doing a histogram, would be. We then connect each one of those dots with a straight line from dot to dot. And then it's fairly typical to draw a line from the first dot to 0 and from the last dot to 0. Sunny, yes, the last two graphs we just showed were histograms. So this is a representation of a polygon. And so you can see at the tails, for example here, we start from 0 and go up to 1, and then at 7, we go back down to 0. And you can again see how this represents the frequency with each one of these points, such that for score 6, we can just go straight up. We see at 6, we had 3 people in whatever that scoring system was that got a 6. Now, what's one thing you notice about the number of dots on the bottom graph? Yeah, so there's not one dot for every number. And so one of the nice things about a polygon type display here is maybe we just didn't collect enough data to give us a really good understanding of what the entire distribution would be. And so we have a dot what looks like over 8, although maybe these are actually grouped together, but let's just say they're not. Let's say this is over 8, and then we have one at 10, maybe. All right, well, we've got one at 10, and we can kind of extrapolate to the value of 9. And so when we talk later in the semester, thank you, Esther, yes. And remember, this is all going to be recorded, and so you also have the opportunity to see it online. And so you can extrapolate, and we'll see this later on in the semester when we talk about things like regression lines that allow you to extrapolate beyond the capacity of your data. Jay asks, how do you know where it connects to 0 if you didn't have any data collected below 4 to 5, like on the second polygon graph? So wherever your first or last data point is, if you collected no more data, you then just draw it down to 0. If you're asking about where would you actually draw that line over, you can see here that for the 0 on the left-hand side of this graph, it's right over 2 to 3. And so because they have grouped these together, you have 4 to 5 as the last data point that they collected, and then it just goes down to 2 to 3. Goes down to 0 over 2 to 3. Does that answer your question? Because the way they grouped it, you have, so the question, I'm sorry. He says, why 2 to 3 and not 3 to 4? Because the way you grouped it, you have 6, 7, you have 4, 5. The next would be 2, 3, just off of the way they have decided to group it. And so in this case, the next group, a histogram. Yeah, okay, perfect. Good to go. So we talked about polygons, we talked about histograms, and then we have our bar graphs. And a bar graph is just like a histogram, except we have gaps between the bars. Now, when might you want to have gaps between the bars? Why would that ever be a good idea? Yeah, so explain that a little bit more. You're exactly right, but for everybody else.
To show that something is not divisible.
Yeah, so, sorry, what was your name? Kenya says that we would do that when the variables are discrete, and that's exactly right. We want to convey that you can't, it's not a continuum. So you don't have real limits, it's just you have an apple, you have an orange. There's no real limit between the two of them. And so whenever you're using measures that rely on a nominal or ordinal scale, you're going to want to use a bar graph. Crap. So you can see here, in whatever personality test we've devised for this example, you have personality A, you have personality B, and you have personality C, but those are completely exclusionary, right? There's no continuum. You're either in A, or you're in B, or you're in C. You can't be between A and B. You can't be between A and C. These are just, you can think about this as personality red, personality blue, and personality pineapple, right? You can do whatever you want. They're just different categories. And so the story we're telling here is that by having this gap in between the bars, you can't have a value here, right? If these bars were touching, the story would be, oh, look, you can have a frequency at that point. But here we're saying, nope, you have a frequency for A, stop, end of sentence, new idea. You have a frequency for B, that's it. And you can't continue on to between A and B or B and C.
So this would be used with the frequency table we made for like who has computer use on this.
Exactly. Yes. Yes, yes, yes. So ACE, right? ACE, so ACE said this would be what we use for when I came up with the example for computers and non-computers, and that's exactly right. Sorry, I know it sounds kind of mundane for me to regurgitate what everybody in this class heard, but I want to make sure that people on the iPad hear. Of course. It's like those of you in the chat have a special conversation between us and are in a special class that the rest of the people don't get to see. You can tell secrets. All right, so we already covered this, but just again to regurgitate, we separate the bars because of the narrative we're telling, right? And that's going to come into play a lot when we get into figures later on in the semester. What is a story we're trying to tell with a correlational design? What is a story we're trying to tell when we do our chi-squared tests, etc.? Good, I'm glad, William. This may be the way we approach it moving forward. You just travel with me like my, I'm not going to say SIRI because I don't want to set off everybody's systems, but you know what I'm trying to say. All right, so what we were talking about to this point were absolute frequencies, right? We knew the number of people who has score 5. We knew the number of kids that were 43 inches tall. But it's often the case that many populations are so large, you can't know the exact number of individuals or the frequency for each of those specific categories. And when that's the case, we can show these population distributions with what's known as relative frequency instead of those absolute frequencies. So let's say we wanted to just represent the overall relationship between bluegill and bass in any big lake. Well, it's going to be impossible to collect every bluegill and every bass in that lake. And so maybe we don't really care about the actual frequency of that sample. We just want to represent, okay, what's the relationship between the frequency of these types of fish? And so even without this disclaimer up in the top right, the first thing you notice is the bar for bluegill is about twice as big as the bar for bass, right? It tells that story. It leaps off the page. So you can see that we would, from that, infer that there are about twice as many bluegill in that lake as there are bass.
Is that tool, these graphs, like signifies 2 times population?
No. That's just for illustrative purposes. Good question. Yeah, when you're doing these relative frequencies, it's rarely the case that you're going to be doing them in an actual scientific paper. They're mostly useful for presentations. And so it's going to be hard sometimes you know, we'll get into things like error bars and confidence intervals and stuff like that throughout the semester. But sometimes it's hard for people to see. And really what you want to hammer home is, okay, what's the relationship between these? What's the relationship between these frequencies? And so this becomes a really good tool for those types of presentations. And so if the scores in a population are measured on an interval or ratio scale, and again, what's an interval or ratio scale? Give me an example.
Interval is like Fahrenheit.
Yes, exactly. So intervals like Fahrenheit in the sense that 0 doesn't really mean anything, but the difference between each point on that scale is the same. And somebody else give me an example of, or a definition of ratio.
It's just a scale where 0 means literally nothing.
Yes, exactly. Yes, just like William said, it's a scale where 0 means nothing, like height. 0 height means you have no height. And I can guarantee on the exam, you're going to get a question for pretty much each one of these asking you to verify what a nominal scale is, ordinal, interval, and ratio.
Can you have negative numbers in a ratio scale?
No. So the question was, can you have 0 or negative numbers on a ratio scale? And I mean, unless I guess you're getting into, you know, theoretical abstract concepts, the answer is no, just because you can't, like negative height wouldn't mean anything in this context. And so if you have negative numbers, that means, that insinuates that 0 isn't really a meaningful 0. Good question. And so it's customary to present this interval or ratio data as a smooth curve rather than kind of that jagged representation of a histogram or a polygon.
Histogram?
What's that?
Can you ask your question again?
Oh, there was no question. I'm sorry. It was just a statement of fact that when you're using a smooth curve, it's for interval or ratio data rather than a histogram or polygon.
Thank you.
Mm-hmm. And so that smooth curve is emphasizing the fact that the distribution isn't showing the exact frequencies, but based off of collecting an adequate amount of data, it's showing kind of the overall trend of it. And so here, for example, we have the population and relative frequencies of IQ in the population. And so you can see that we don't have exact frequencies for each one of these, but you get a pretty good idea. And as we'll talk about later, I think next week, you get a pretty good idea that roughly about 2/3 of the population falls in between an IQ of 85 and 115. All right, so just looking at that relative frequency, it is much more likely that you have an IQ of 100 than you have an IQ of 85 or 115. Just if we pulled random people out, not saying you specifically. This is kind of just regurgitating what I've already said. The graphs are really kind of showing in a quick and easy way at a glance what's the highest score, what's the lowest score, what's kind of the average score, what's the distribution of the scores. All right, so I just showed you kind of that smoothed over graph for IQ. And a graph is going to show that shape of the distribution. A distribution is symmetrical if the left side of that graph is roughly, more or less, a mirror image of the right side. So if we go back to IQ here, you can see that if we draw a line right down the middle, very not straight line there, let's pretend that's a straight line right down the middle, the left side could be flipped over and represent that right side, right? One example of a symmetrical distribution is what I just showed with IQ. And we call that a bell curve, because it in fact looks like an old-timey bell, right? So that's a bell curve. More specifically, we would call it a normally distributed or symmetrical distribution, normally distributed bell curve. There are some things in life that are in fact normally distributed, but there are a lot of things in life that aren't. And when they're not evenly distributed in the way IQ is, we call those distributions skewed. And it leaves kind of a tail, is what we call it. So in a positively skewed distribution, these scores tend to pile up on the left side of the distribution with the tail hanging out on the right side. I'll show some examples of this in just a second. And a negatively skewed distribution is just the opposite of that. So the scores tend to pile up on the right side, and the tail hangs out on the left. It's really important to remember in this class that when we say things like positive and negative, these aren't value judgments. They're indicating directionality, right? So a positively skewed distribution is not a good distribution, in the same way that a negative skewed distribution is not a bad distribution. And then when we get into correlations, we'll talk about positive and negative correlations. Those aren't good and bad correlations. It's just referring to the directionality. And I can guarantee that's going to come up on your exam too. Not that I'm teaching to the exam, but. All right, so on top, we have two representations of a symmetrical distribution. So on the left-hand side, that's our bell curve. Symmetrical, draw the line right down the middle, flip it over, it's the exact same. On the right-hand side, symmetrical right down the middle there. We call this a bimodal distribution. So an example of a bimodal distribution would likely be height in the population, because women tend to be, I think, like 5'7", 5'8". Men tend to be around 6 feet tall. And so you get these clusterings. You do have some women that are going to fall way over here or even further. You do have some men that are going to fall down here or even further. But in general, you have the clustering here and you've got a clustering there. And even though it's symmetrical, it's a different type, and we don't call that a bell curve. And then on the bottom is the representation of the positive skews and the negative skews of data. So you can see the positive skew, you've got most of the data hanging out here on the left, and then it kind of trails off on the right. So who can think of a real world example of something that is positively skewed? Yeah.
We do like most gymnasts are really short, so if you did like a sample size of like Olympic athletes or Olympic gymnasts, they're all gonna be shorter versus taller.
Exactly. Yeah, so if y'all couldn't hear, the height of gymnast would be a good example, because a lot of the gymnasts tend to be, what's the average height of a gymnast?
In trampoline, it's like under 5'5".
Under 5'5". So yeah, so we'll say, this ranges from, 4'10". That was awful. But then you could have some gymnasts who are just freak athletes, even though they're much taller. And so you get a couple down here that are, 5'7" and taller. Are you a gymnast?
Yes.
Well, there may be a time where we ask you to do like a back handspring or something in front of class. We'll figure out when's appropriate, but. All right. Jay says, average age of natural death, old age. Exactly, yeah. So you would have, your average age of death in here, let's say 85. You are gonna have some people that die, of old age at 70 or younger. But then you also have the outliers that live to 115, 120. Not many, but you do have people that live that long. All right, who can give me an example of something that has a negative skew? A really easy test, exactly, yes. So if I were a nice professor, which I'm not, and I gave you a really easy statistics exam, and the average came out to be, let's say, 98%, you're still gonna probably have a couple people who just didn't watch any of the lectures, didn't put in any effort, and still get, a 30%. Exactly, very good example. Questions about skew? Yeah.
Isn't there, like, what happens when it's not a big curve?
When it's flat?
Yeah.
Yeah, very good question. So the question is, what happens when it's flat? And you could still call that a normal distribution. It may not be a bell curve. When we talk about variance and standard deviation, we'll actually go over that a little bit more. But yeah, you would still have kind of a symmetrical distribution in there. You wouldn't call it skewed so long as it is, in fact, symmetrical, even if it's flat. Very good question. Any other questions? Awesome. Rocking and rolling. And so the relative location of an individual or individual scores within a distribution can be described by percentiles or percentile ranks. So I don't know if any of y'all have kids in here, but once you have kids, you'll take them to the pediatrician. And as they start growing up, you'll get things like, little Johnny's in the 95th percentile for height. And what does that mean? That means we've now compared little Johnny's height to everybody else his age. It says, okay, he's likely going to be taller than 95% of the male population. Right? And we can do that once we know the population baseline. We can get a pretty good idea of how things play out across the different percentile ranks. And so you'll have your percentile rank for that particular value. And so when you took the SAT or the ACT, you not only got your score, but you also probably got a percentile. You're in the 98th percentile. You're in the 72nd percentile. And what that means, that percentile value is the percentage of people who scored below on that test. So if I say you're in the 30th percentile of something, that means 30% of people have values lower than you, and 70% of people have values higher than you. And so there are a variety of ways to go about getting those percentiles and percentile ranks. But to find the percentiles and percentile ranks, you create two new columns on your frequency table. One for cumulative frequency, and the other for cumulative percent. And once you do that, each cumulative percent identifies the percentile rank for the upper real limit of that score. However, when you have scores or percentages that don't correspond to those upper real limits or cumulative percentages, you have to use what's known as interpolation. Interpolation is just a mathematical process based on an assumption that the scores are going to change in a predictable, linear fashion as you move from one end to the other. So you're making certain assumptions about the data to get those percentiles. No. So we will, yeah, that's a good question, but no. Oops, I split this up. That didn't work. So take, for example, is anybody in here a runner? Good, because running's stupid. Don't run. Let's say you all were runners. And you went out on a 2-mile run, and you timed it at 40 minutes. Let's say you're having a really bad day, and you decided to walk instead of actually run. And you wanted to know, okay, what was my actual split on that, on each one of those miles, or each one of the half miles? Well, you don't know how or what time you crossed that 1 mile mark, or what time you crossed that 1.5 mile mark. But based off of the fact that you know your end time and you know your end distance, you can start trying to extrapolate what was the actual time it took you to run the first half mile. All right? And so we have our known values here of 0. We have our known values here at the end. And so now we can just split it up. So let's split it in half. Half would be 1 mile. What was the time at that 1 mile? 1/2 of 40 gives us 20. So it took us 20 minutes to run that first mile. Right? We're making assumptions about the data that you ran at a regular, constant, predictable speed, and that there weren't massive fluctuations. Right? I mean, you can think of a real-world example where you go out to run 2 miles, and a mile in, you break your leg, and so now you're hobbling. Maybe that first mile you ran in 6 minutes, but it takes you now 34 minutes to get back home with the broken leg. These sort of assumptions don't factor in things like that. We're assuming that nothing like a broken leg happened on your run, and you ran at a constant speed. And so you can see limitations to this sort of interpolation process, but you can still see how it would be useful. All right, and the last thing we're going to talk about today are stem and leaf displays. And I'm sure you all have at least seen stem and leaf displays. But it's a very efficient way to kind of display that same frequency data. And so we divide every score into what's known as its stem and its leaf. So let's say we were doing ages in here. Well, there still may be some of y'all who are under 20. They're old farts like me who are over 20. And so we will establish everybody's age. And now we're going to take off the tens column and make those our stems. So now on the stems, and I'll show you an example in just a second, but now on the stems for that table, we have 1, 2, and 3, right? Representing 10, 20, and 30. And then we take the ones column and put that in the leaves. And so if you're 19, you would fall under the 1 for the stem, and we put a 9 on a leaf. If you're 25, it would go under the 2, and then a 5. And so this is what that looks like. So we have all of this data over here on the left-hand side, and we're going to organize it. So you can see we've split each one of these data points. We've removed the ones column from the tens column. And so here are all those values in the 30s. So let's go look for the 30s. Looks like we've got a 32. We've got at 33, and it looks like that's it, right? So we've got 2 values. So create that 3 for the stem, and now we put 2 and 3 in the leaf column. If we go down to 7, so in the 70s, you can see we've got a lot of values. And what's something you notice about those values? Yeah, they're not in numerical order. So first thing you're doing is just taking the data as it comes. What's another thing you notice about the data? It does look at one big number, yes. But you're also repeating some of these, right? And so you're not just doing it, you're not just saying 76 once, if there are multiple 76s. This is allowing you to get an idea of the relative frequency of each of these numbers, or each of these stems, the leaves rather, for each of these stems. But you're also not just putting the number once, because you really want to, yes, 6 is in there twice, and 4, absolutely, Amber. And so you want to represent every individual data point, because again, the purpose here is to give the frequency, right? You're not just saying, okay, what values were collected. You want the actual frequency for each value. Questions about that or anything we covered today? Yes, ma'am.
Does it matter, like, what order we put the numbers in on, like, the, I guess, the leaf side?
So you mean, so for like 3, does it matter if 2 or 3 comes first? So it's typically the case that the first one that comes up as you sort through the data is the first one you put. So you would start up here at the top left, and I mean, it would depend on how you actually went it. No. That's just kind of the standard. Other questions? Awesome. Well, thank you all for a good first strange week of stats during COVID. Next time, we're going to talk about central tendency. Make sure to read chapter 3. I will see this group next Thursday. I will see those of y'all on Zoom who come to class on Tuesday, Monday, Wednesday, whatever day it is. Yes. I will see, God, is it really only Wednesday? Jesus. Yes, just kidding. I will see y'all on Wednesday. Thanks for ruining my week here.
Sorry. When I printed this out, not all of the other written things were on there. So I just wanted to let you know that I wanted to write those in, the things that are missing on here. You know what
Okay.
I'm talking about?
Yeah,
So
yeah.
that way you know I'm not here. Okay.
Thank you.
I need to ask you this last semester, where do you train?
For jiu-jitsu?
Yeah.
At Maverick downtown. So do you know where Clinton Avenue is?
I don't even have a car here, so.
Oh, okay. So yeah, it's just right downtown. It's like 5 minutes away from here. They are still open at this point. I have not been going of late, just because it seems like rolling around would be a great place during coronavirus. But yeah, it's a place to do Muay Thai there as well.
Excuse me.
Oh, yes, Sonny.
I wanted to ask about the stem and leaf stuff. So like what do you use it for? Like I don't know. Because I've never seen it before, so I'm not sure what the use for it is.
What, for the stem and leaf plot?
Yeah.
Yeah, so the stem and leaf plot you use for just kind of representing the data. So anytime you'd be using a histogram, it's a stem and leaf plot. But it's just kind of another way to represent